Hello, this is Professor Salahat, and in this video we're going to work on homework 7. And homework 7 is chapter 9 from your book. And the first question we're going to look at is number 1 here. Two variables have a positive linear correlation. Does the independent variable increase or decrease as the dependent variable increases? Notice one very important word in here says positive. Again, we're talking about linear correlation, but we're talking about positive. In other words, this is what we are looking at. As x goes up, y goes up also. So it looks like this. That is positive. So if it's positive, the x is the independent and y is the dependent. So in this case, two variables have a positive linear correlation, means the dependent variable, again, as one increases, what will happen here? It says, as the dependent variable increases. Okay, or does the dependent variable increases? And the question in here is about y. What will happen to y as the dependent variable increases, as x increases? So what will happen to y as x goes up? We know that in this case, the dependent variable will also increase, which is part B, or the second one. As the independent variable goes up, the dependent variable will go up also. So that's the answer. Next one is, now we are looking at here, we are looking at two terms that we like to pay attention to in statistics, and that is R, and there is another one is called rho. It's look like this. Now, both R and rho are about, they both calculate for us what we call the correlation coefficient. But notice that R deals with sample, and rho, and in this case here, the rho deals with population. So if I'm trying to find if there is a relationship or correlation between two things, for example, about homes in a certain town, I cannot just go and survey all the homes. I will pick a sample, and if I'm working with a sample, then the R I calculate is called R, or the correlation coefficient. Now, let's say that I'm in a small town where there's only 50 homes. I can really survey all 50 homes and compare their price to the size of the home. And in this case, I'm coming up with something called rho. So the R represents the sample correlation coefficient, and the rho represents the population coefficient or correlation coefficient. Okay, we're not talking about critical values in here. So we'll check, and that's the correct answer. Now, here, maybe I need to expand this, and maybe I need to minimize the window a little bit to see everything. Now, in here, they tell us to drag the correlation that fits the definition here. Now, there is a picture and there is a definition. The first one in here, in the bottom here, it says perfect positive linear correlation. Look in here and see which one is positive, and it is perfect. I see this one here is positive. So just click on it and press the mouse down and drag, drag, drag. And when you get into that box, just release. Now, if it doesn't happen, try it a couple of times. Now, so this is a perfect. Why perfect? Because it's a straight line. Perfect. And it's positive going up. The one after is strong positive linear. By the way, let's look at this. This one in here, which is the second one in here. It is coming down, so it is negative. It is not coming down in a straight line, but it's close enough. So in this case, we say it's not perfect, but it is strong, and it's coming down, it's negative. So this is a strong negative. Which one is strong negative? Here. So we bring it down here, because that is strong negative linear correlation. It is coming down. That's the reason why we call it negative. And it's not coming down in a perfect way, but it also it's not in a sloppy way. It is close enough, so we're going to say strong negative. Now, notice that this one in here, and this one, those two here are not linear. I don't care. This one is messy because we can't tell if it's going up and down, and this is curved. Either way, it doesn't matter. They are not linear. So we're not talking about linear because this here talks about linear. I'm highlighting this, and this talks about linear. So we're not talking about linearly. We are only talking about no linear. So both of those two will go in here. So this one will go in here, and the next one, just drop it above it, they fit. So no linear. Those two are not linear. This one in here is strong native coming down, and this is perfect going up. So when we check, let me hide this, check, and that will be okay. Now, the one after that, it says identify the explanatory variable and the response variable. Notice and again, let me minimize this a little bit and talk a little bit in here. In statistics, there are two variables in this class. In correlation, there are two variables, x and x. We call that, again, we use x to explain, okay, y. Therefore, y is the response always, and x is the variable that explains the y. So in this case, let's read the problem here. It says a golfer wants to determine if the number of lessons received every year can be used to predict the amount of improvement in his game. So we are looking at the number of lessons as a way to see if did he improve or not. So the improvement is y. So the response variable is the improvement. Amount of improvement will be the response, and that the amount of improvement depends on what? Number of lessons. So the number of lessons can explain, like if somebody says, hey, I didn't improve, you can tell them, hey, you didn't practice enough, you didn't take enough lessons. So the number of lessons can explain the improvement. In this case, again, here it is the independent, and this is the dependent. So the number of or the amount of improvement depends, it's a dependent on the number of lessons. So we're going to check this answer, go to the next one. Here, we need to be careful because in here it's not looking really at if there is strong correlation or not strong correlation, whatever. Here it says the scatter plots below, all of them show the result of a survey of 20 randomly selected males aged 24 to 35. Using age, we're going to use age as the explanatory variable. In other words, we're going to use the age as x. So look at the bottom here, age, 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 all of them age. The question in here, what is the y-axis? Now we want to survey 24 to 35, age 24 to 35, 20 randomly selected males, and we asked some questions. We asked them 4 questions. The first question is about what? There is a unit in here, but didn't tell me what. The second says thousands of units. The third says units. The fourth says thousands of units. Let's look in here because this will guide us in here. This says age and body temperature. So look at the y-axis. Which one represents body temperature? It cannot be the second one because it's in thousands. It cannot be the last one because it's in thousands. So let's look between the first and the third. On the first one, the body temperature is around 100, which is, acceptable because it ranges around a little bit under 100, around 100, that number. But look at number 3. Number 3, if this is number 3 is the temperature is going to be between 65 to under 80, and that's not acceptable because for human beings, the temperature is not acceptable in that range. So we're going to drag this and we're going to put it here. So we drag the first graph and we put it there because it talks about body temperature. Now, let's look at the height. Height is not in thousands, by the way, so it must be this one because the height of those people can be between 65 inches to under 80 inches. Okay. Now, what about the second two? One talks about age and balance on a student loan. One talks about age and income. Notice that any of those two would work because in thousands of dollars. But let's look at the most common or the one that makes sense more. So I would predict that student loans can be zero. I'm going to put this in here because some people have no student loan and some people have like around 45,000 and somewhere in between. Where income can be here, I'm going to put this income in here. Income can be between around like under 20,000 to close to 20 or 95,000, something like that. So this is just my guess on those two. They are close, but it makes sense to go from 0 to 45 for a student loan, and it makes sense to go from 18 to under 100 for income. So let me check, and it's a correct answer. Number 6 is asking us to calculate. Again, they give us data in here, and they say the age of 10 men and their systolic blood pressure in millimeters of mercury are shown in the attached table. So there is a table. If I click in here, there is a table, and it shows me the outcomes, the age of 10 people, and what is the measure of the systolic blood pressure. In this question in here, they tell us in here that with a sample correlation coefficient R, so they already calculated R for us. They told us R is equal to 0.898. Again, it is here. They stated R for us. It says remove the data entry for the man who is 48 years old. So there is the man, 48 years old. We're going to remove the reading in there because it could be wrong. Because notice that the 45 has 134 and the 63 has 184. So the one in between has higher blood pressure than both. So it could be a mistake. Let's remove that. So let me go copy this data into StatCrunch. Here, I'm going to click in here. Open StatCrunch. I'm going to put my data into StatCrunch. Then after that, they told me to remove this man with the 48. So I'm going to click on the 48, remove it, and click on 201, remove it. I'm going to click the age of the man and his blood pressure. Completely, that man is gone now from my calculations. So the next step is they ask me to calculate his R. So to calculate R, we go to Stat, we go to Regression, Symbol Linear, click. Then the X variable, and let's go with this. The X variable will be age, which is age. And the Y variable will be systolic blood pressure. And just don't do anything in here, just go to commute. And this is the R that we got. And they want the R, let me close this, I don't need it. They want the R only to, again, in here they say the new correlation coefficient R. Let me copy this R here. The new R is equal to 0.9716, which is roughly 0.972. Okay, so this is the new R. So let me just put this down. I'll leave it alone. They say the new correlation coefficient R gets stronger, gets weaker, or stays the same. Notice that we went from this number to this number. So the number is now larger. It gets larger. If it gets larger, it means it gets stronger. So in this case, we're going to choose stronger. And going from this 0.898 to 0.972. Now, when we check the answer, it's going to give us a correct answer. And the reason is, and the reason why it's getting stronger, notice that when we try to graph the dots, that's what we call scatter plot. The man who is 48 years old has a blood pressure of unusual blood pressure. So his blood pressure is somewhere here. And it is far away from the rest. Like, again, here is the line. Let me drag this back. Now, if we have a line, here's the line of best fit. And notice that this dot is far away from this line, way far away from the line. Like this distance is too big. Now this, what will happen is it's going to pull the line and is going to make the line, this is what we call in statistics an outlier. An outlier will ruin our data, will make it weaker. So when we remove this outlier, what will happen to the line? The line will try to it will have a better R, which is a better representation. It is going to represent the data better. And the reason is because that value is probably a mistake. So let me go back in here. So that's the reason why this number in here gets stronger. Now I'm going to skip number 7, and I'm going to look at number 8. Number 8 is the same concept. They tell you in here we collected data row 1 or row 2, and the row 1 and row 2 represent things. Maybe it is the age, and maybe it is something else in here. They didn't tell me exactly what the story. Maybe age and maybe the number of books read or something like that. Okay, so in this case they tell us calculate the correlation coefficient R, letting row 1 represents the X value and row 2 represents the Y value. So in this case I'm going to copy this into StatCrunch, and notice that while here it's in StatCrunch, I'm going to go to Stat, I'm going to go to Regression, Symbol Linear, and they tell me here to let row 1 represents the X and row 2 to represent the Y. And they ask me to find the R. So when I find the R, here is the R, and they want the R rounded to 3 decimal places. Notice it's native 0.227, native 0.227. Okay, now when I check the answer, it tells me it's a correct answer. The second time in here, they say calculate the correlation coefficient R, letting row 2 represent the X and row 1 represents the Y. So in this case, they tell me, let's repeat this. Stat, regression, linear. But when you come in here, when you choose the X, don't choose row 1, choose row 2. When you choose the Y, don't choose row 2, choose row 1. So flip them. And what happens in here? Look at R. Here is the R, and we get the same number, native 0.227. So it is the same number in here that we got. And this is clear because R is a measure of the strength of the correlation or relationship. So the relationship between two things, row 1, row 2, or you can say row 2, row 1. It doesn't matter. So the relationship is the same. That if you flip the columns, by the way, if you flip the columns, R is the same. But if you flip the columns, other results will vary, will be different. So be careful, okay? And we should not flip the rows unless we are told to do so. But in the future, with the future problems, we have to be careful. Which one is going to be row 1? Usually row 1 is X or the independent variable, and row 2 is Y or the dependent variable. Don't flip them. But in here, they told you to flip them just to measure R. Notice that if you flip them, R will be the same, but the equation, which is what we care about the most, here is the equation. If you flip them, the equation will be different. So that's the reason why we have to be careful. So now the number or the problem after that in here, it says what effect this in this case we can say remains unchanged. Just to finish this problem, they don't change. The question after that will be here. Is two variables have positive linear correlation. In other words, let me put this down. Two variables have, if I draw a picture, now they look like this, dots going up. So there is a positive linear correlation. So is the slope of the regression line for the variable positive or negative? Notice that from algebra, when you guys learned algebra, by definition, slope is rise over run. So the slope is the rise over run. Notice that the slope in here, because the line is going up, the slope will be positive because the rise will be positive and the run will be positive. Again, when you go from here to there, we go moving positive direction. And when you go up, we are going positive direction. So a positive over a positive is positive. So therefore, the slope is going to be equal to a positive number. So if the, and that is, you should pay attention to that because it helps down the road. If the slope, if the relationship, the correlation is positive, the slope will be positive. So the slope is negative in part A, no. The slope is positive in part B. The slope is negative in part C, and the slope is positive in part D. So you have to choose between B or D. So let's read. It says in B, it says the slope is positive as the independent variable increases, the dependent variable tends to decrease. And then here in part D, it tells you as one goes up, the other one goes down. And that's not true. As you see from the picture, as one goes up, the other one goes down. Or goes up, sorry. So this is not correct. This means as one goes up, the other one goes up. So that is part D. The slope is positive as the independent variable increases. The dependent variable also tends to increase. So that is correct. So with this, I'm going to stop here. And we're going to try to, or we'll try to do another video soon.